Hello, everybody, and welcome to this discussion on the neuronal action potential. So before we get started, let's just talk a little bit about what does this mean in general? Well, you see here the graph, and we're going to go through this throughout this discussion here. And what we're referring to is an action potential, which is a method of propagating a signal down a neuron, propagating an electrical signal down a neuron. And in the end, this is how all our neurons communicate with each other, communicate with our organs and muscles, right? There's two ways that this can start, a chemical or an electrical start to the action potential. And when we say chemical, that means a neurotransmitter starts it, or an electrical would be an ion starting it. Remember, ions positively charged, negatively charged can start this as well. And when you have a chemical neurotransmitter starting this, it's going to trigger an electrical process. So on the right here is what we're seeing is the graph of an action potential over time as it propagates. So what it means is within the neuron, we generally start at a negative potential, and then throughout the action potential, you get a spike positively and then a return to the baseline negative. So let's go through what this is. But before we do that, let's talk a little bit about the neuron itself, what it looks like and how it relates to the action potential. So here's a neuron, and we'll go left to right here. So on the left, you see all these kind of like spider leg-like extrusions from what is the cell body. And these are the dendrites, all of these lines coming off of it. These are dendrites, and that's where a neuron receives its signal, right? So a neurotransmitter or an ion will start the action potential by hitting these dendrites. And here you have the cell body, which in a neuron is called the soma, the nucleus as well. And then this is really the business end of things here. So this long, thin tail is the axon, and this is the direction that the action potential propagates. So you can see the arrow here goes down this way, and then down here is the axon terminal, and then it'll synapse to another neuron or the muscle or the organ, whatever it is synapsing on. So starts over here, and the action potential propagates this direction. A few other things to note. The beginning of the axon is known as the axon hillock, and then you have myelin sheath, right? So myelin is made out of schwann cells or oligodendrocytes, or the myelin is made out of schwann cells or oligodendrocytes, depending on if it's the peripheral or the central nervous system, and that allows the signal to propagate faster. And between the myelin is the nodes of Ranvier, and that is where the action potential jumps from. So that propagates this way, synapse, and there you go. So before we really get into the steps here, one thing I want to mention about the sodium channels, and sodium channels are a huge part of this, which you'll see, but there's three states that they can be in. Number one is the activated state, two is the closed state, and number three is the inactivated state. But what is the difference between these? Well, activated is just as it sounds. Ions can freely pass through the sodium channel. But inactivated, the ions can't pass through and it cannot be activated. So let's explain this a little bit, because if it's closed, the ions can't pass through, but it can be activated. So in other words, a closed sodium channel can be activated, but an inactivated channel cannot. So how would an inactivated channel become activated? Well, the inactivated channel must be closed, and then the channel can become activated. So a little semantics and a little confusing, but I think if you read through this once or twice, you'll get it. Okay, so let's start with understanding what the resting membrane potential really means. What are we referring to here? So on the left side of the screen is the extracellular, ECF area, and here on the right side is intracellular. So this is inside the neuron, this is outside the neuron. Well, you'll notice here, starting on the intracellular side, we have predominantly potassium as our positive ion. That's a big player on the intracellular side of things. And A- over here refers to just a mixed bag of negative ions. On the extracellular side, you have calcium, positively charged, sodium, positively charged, and then chloride, which is negatively charged. And when you look at the difference overall in charges, extracellularly compared to intracellularly, the intracellular neuron has a net negative charge, and that's at about negative 70 millivolts. And that's important as we start the action potential. And then on the membrane, you can see there's a bunch of different transporters that can transport all these ions. You have potassium channels, your sodium-potassium ATPase, your sodium channel, and then the receptor that your neurotransmitter is going to bind to. So let's get started here. What's the first step? Well, the first step is just being at the resting potential before or after an action potential occurs. So we have our graph here on the left, and we have our diagram of the cell membrane and what's going on here on the right. So on the left, the resting potential right here. So we're resting comfortably at minus 70 millivolts, roughly. And we're at equilibrium here. So what's going to be happening at the resting potential is your sodium-potassium ATPase is actively transporting sodium and potassium across the membrane to maintain the resting potential. And so when we look at that, you have your potassium being pumped in, your sodium being pumped out. I always remembered the sodium-potassium ATPase by thinking of the word pumpkin. If you pump K in, you pump potassium in, and then you can just tell it's sodium out, potassium in. So that's what we're doing here at the resting potential. What happens next is initial depolarization. So on our graph here, that's this little beginning spike up in the potential here. And what's happening in initial depolarization is your neurotransmitter binds the receptor on the dendrites, and then that activates a ligand-gated sodium channel. So looking here, just like we said, your neurotransmitter binds to the neurotransmitter receptor, which then activates the ligand-gated sodium channel. The ligand here would be the neurotransmitter. And then your sodium starts to come into the cell. And we say this is initial depolarization because you just get a little bit of depolarization. You go from about minus 70 to minus 55 millivolts, and that's what's shown here, right? Just a little bit. We're not getting that huge spike yet. Then we get the rapid depolarization, right? And that's when we get this really big positive spike in the membrane potential. And what's happening here is your intracellular threshold potential is reached, triggering a rapid propagation of sodium channels, opening down the axon, causing this rapid depolarization. So what this means is once you get to that point of around minus 55, your voltage-gated sodium channels, remember these are now voltage-gated, open up, and you get this tremendous influx of sodium. And that's why you get this very steep shoot up in the membrane potential. And we go from about minus 55 to around plus 30. So a difference of almost 80 millivolts, right? Over 80 millivolts. And so once we reach that peak, we start to repolarize. So repolarization here is when we come back down, and the sodium channels are then inactivated. Remember the difference between inactivated, activated, and closed. And the potassium channels open, and potassium comes out of the cell. So what that looks like, the sodium channel becomes closed, the potassium channel opens, potassium comes out. If you're moving a positive ion out of the cell, you're going to become more negative in the cell, right? So we go from about plus 30, we're at the peak here, and we go down and we actually end up hyperpolarizing, meaning we overshoot a little bit. So we go down to about negative 75. Hyperpolarization, like we said, so instead of going from plus 30 down to the resting potential at minus 70, the hyperpolarization just means that we overshoot that a little bit and then return to the baseline resting potential. So the potassium efflux slightly overshoots the resting potential, and then the potassium channels close and we get back to that minus 70 resting potential equilibrium. So we go from the hyperpolarization point, which is about minus 75, to the resting potential equilibrium, which is minus 70. And that's the end of the action potential, right? Let's talk about a clinical correlation here. Well, what if a toxin inhibited the sodium channels? So like we see here, your sodium channel doesn't work. Then you're in big trouble, right? And this does exist, something called tetrodotoxin or TTX. There's some others, ciguatoxin, saxitoxin, but TTX is the main one to know. And it's an interesting one because it actually comes from the pufferfish. Some cultures in some areas of the world, pufferfish is a delicacy, but it has to be prepared very carefully. Otherwise, you can end up consuming the toxin. And so what happens there, the toxin blocks your sodium channels. Well, you're in big trouble, right? Because then your action potentials can't occur properly. Your neurons can't communicate. Your muscles and organs can't communicate with the brain. Nothing's going to work here. So You might initially have some numbness, weakness in the face and your distal extremities, fingers, toes, things like that. But if you really have enough of this toxin, that's when you get into big trouble because then your diaphragm starts to fail, which means respiratory collapse, and you'll need a tremendous amount of supportive care. I say supportive care because there is no known antidote or cure for this. You kind of just have to ride it out until the toxin eventually lets go of the channel if you're able to survive that long. Let's just talk about some prime points here. These are things that can be tested on and that I think are a little bit more important. Remember, the neuronal sodium channels have the 3 states that we mentioned: activated, inactivated, and closed. The inactivated state needs to become closed before becoming activated. You can't go from inactivated to activated. You have to go inactivated, closed, activated. The synapse occurs at the dendrites, and then the action potential propagates down the axon to the axon terminals. And then finally, the action potential is primarily driven by sodium influx and potassium efflux. So that's a big testing point, right? Know that the depolarization is due to sodium influx and the repolarization is due to potassium efflux. That's definitely something that can be tested on. And so that's the end of the discussion here. I hope that that was helpful and kind of clarified this and the steps of the action potential. It's definitely something that can be high yield on medical school exams and not so much in residency, but it helps to just understand these kind of fundamentals of physiology.